We'll spend a lot of time in this course talking about change processes and how they affect systems, and in particular how we can track energy exchanges that occur during the course of a system, during the course of a change process. So one of the things that we're going to need to do is to talk about how energy content in a system can be tracked. Now, one advantage that we have with this is that energy is a property of a state of a system. So, in other words, this is something that is tied to what we know about a system from its system properties, and there's another important consequence of this, and that is that the change in energy depends only upon the state at the beginning and the state at the end. So delta E is something that we can define if we know both the initial and the final states. Another way we could write this is to say that delta E is simply equal to E final minus E initial. All right, so what we do is we have anything that can be described this way, where it is simply a consequence of the state that we happen to be in, is we call this a state function. And state functions are at the heart of all thermodynamics. In fact, we're going to care a lot about whether something is a state function or it's not a state function. But in this case, our energy is going to represent a state function and something that we can rely upon if we simply know where the system starts and where it ends. Now, this has not always been known, not always been the case. And in fact, in the 1800s, there were a whole series of experiments that were done primarily by Joule and by others to try and measure what role work and heat played in this. And one of their or I guess there are many consequences of that work, but one of the things that was learned is that heat, which we're going to label with Q, little q, and work, which we'll label with little w, that these are in fact equivalent in some ways in the sense that they can be exchanged with one another. In other words, heat can be used to generate work, and work can be used to generate heat. This was an important discovery because it gave them some insight into how energy changes can occur in systems. And this insight actually was very important in formulating something that we'll call the first law. Now, before I get to the first law, though, I want to mention that the energy that we're going to be talking about for systems, I'll call this the total energy, and I've been labeling it E so far, has several components to it. And one of these is the kinetic energy of the whole system. So I'll call that E kin / cis. So in other words, if your system is actually moving around in the universe, it has kinetic energy. But what we don't care about isn't this movement of the entire system, but something more internal to the system. Now, I could also say that that entire system could be subject to some field, a gravitational field or an electromagnetic field. These are things that are affecting the whole system and not necessarily the qualities on the interior of the system. We're going to separate those out, and I'll call that E internal, as to what's happening in the system itself. So we're going to care less about these elements of the internal energy, these elements of the system energy, and really focus on this part. And I'm going to give it a special letter. I'm going to call it U. So whenever you see U, what I'm talking about is the internal energy of the system. I'm not talking about the movement of the system altogether, but the movement of the parts of the system inside. So the net result of all of Joule's experiments and others was the conservation of energy written in this form. Basically, that the change in energy was equal to the contributions of heat and work. And this is what really came down to be called the first law of thermodynamics. And I'm going to run out of space. All right, first law of thermodynamics, and we're going to basically encapsulate it this way. All right, so it refers to the conservation of energy, and I will tell you, I wasn't always sure why they would equate this with conservation of energy. But what it really has to do with is the energy of the universe is the thing that is conserved, and the system is exchanging energy with the surroundings of it, and in the way it's exchanging that energy is through the mechanism of heat and work. So they are interactions that allow the system to change energy with the universe, but because energy is conserved, we can basically limit it to just that. All right, so we're going to first care about small infinitesimal changes that occur in a system. And small infinitesimal changes we're going to denote like this, with a little du, like a derivative. All right, so it's like a small differential change in the internal energy. Now, I'm going to make the further claim that this internal energy is a state function, and that's what allows us to write a small incremental change as a differential. But the tricky part here is that this small incremental change in the internal energy comes about from a small incremental change in heat along with a small incremental change in work. Now you'll notice I wrote those d's differently. I wrote them actually as Greek deltas. And the reason I did this is because Q and W are not state functions. So we can't treat them as a differential in the same way that we treat the energy as a differential. And the key difference here is that these incremental changes depend upon the path the system takes. In other words, you could achieve the same differential change in energy through lots of different combinations of heat and work incremental change. So let me sort of formalize this and say that this little delta Q is going to be the incremental change in heat, but it is it depends, if you will, on the path that's taken by the system. Similarly, delta W is the incremental change in work. And this again depends on the path. And because these things depend on the path, we have a special name for them. We're going to call these things path functions. And what that means effectively is that we can't use the same sort of statement that we've given up here and especially up here. These are not true of path functions. So I can't just say that the total heat is equal to some integral over this incremental change in heat unless I happen to know the path that the system followed in doing that incremental change in heat. Similarly, I can't say that. I can't say that the work that's generated is just some integral over these incremental changes in work. Those are simply not true for these. Now, I want to say a couple of other little small things about this. The work that we're going to deal with is mostly due to mechanical work. And so mechanical work in this case, we can write as a change in the pressure times volume. So we're going to draw the incremental dW as minus P dV. Okay, now volume is a state function, but because pressure can depend upon volume, that's why we can't simply write that work is equal to the integral of P dV, because we don't necessarily know what function of volume the pressure is. That is going to depend upon the path that the system takes. So the key lesson here is that we cannot treat work and heat as though they are state functions. They are path functions. We can treat the internal energy as a state function. And I guess the final word on that is that we can ultimately write a change in a state function is equal to the integral from state 1 to state 2 of du, which means that it can be written as u2 minus u1. So any function that you can write in this way is going to basically represent a state function.